Hi, welcome you all for the serial communication protocol. This is the continuation video of I2c protocol. In previous video, in part 1, we have discussed till the I2c communication frame format, and in that we have discussed how the write operation and how the read operation is done and how would be the frame format in write operation and read operation. So let's move on to the next topic. Start and stop condition. If you see here, when I am doing write operation as well as read operation, it obviously start with the start condition and stop condition. Okay, how the start condition and stop conditions are identified means it has some specific rules. Like SD is nothing but data line and S clock is clock line. Okay, the start condition is nothing but my data line goes low while my clock is high. Could you note here, this is my clock. My clock is high. During my clock is high, my data line goes from high to low. So this denotes the start condition. As well as if you go with the stop condition, while my clock is high, serial clock is high, my data line goes from high to low. Okay, this is our clock. My clock is in high state. During the high state, my data line goes from low to high. Hence, it is called a stop condition. So, this state change is happening in clock and data, then it will be considered start condition as well as stop condition. Because by using this only, we can, confirm that it is the beginning or ending of the communications. ACK is nothing but receivers pull our data line into low. Obviously, it will be in high state. During the acknowledgement, it will be pulled to low, which indicates that it is ACK received, and also it tells that the reception is successfully happened. NACK means my data line will remain in high state instead of going to low state. It indicates that failure or end of communication. In which case it denotes failure. If I am doing the write operation at the time, my not a NACK will be used to indicate that transaction is failure. End of communication during our, see here, during our read operation, last bit is read, then it will give NACK. Okay, hence I have declared indicates failure case in write operation, end of communication in our read operation. Is it clear? Okay. Now, data transfer in I2c. How the data transfer will be in I2c? Data transfers are generally transferred bit by bit because it is serial communication protocol. Okay, as well as it transmit MSB first. MSB is transmitted first, which will be followed till its LSB. As well as data changes only when our clock is low. If our clock is high, then data sampling will be happen. Okay, when will be data sampling happen? When our clock is high, data sampling will be happen. If my clock is low, at the time data changes will be happen. Then how will be the read and the write operation? How will be the read and the write operation? So write operation is nothing but my master sends the data to our slave. So it contains slave address and then data bytes. Okay, so write operation is nothing but master sending data to my slave, which consists of slave address as well as the data bytes. Read operation, master want to read the data from the slave. So what master will do? Master requests data from the slave and then slave will transmit the data to the master. Okay, here master is sending, so it sends the slave address as well as the data bytes. Here master wants to read the data from the sensor, so it requests the data from the slave. Slave will transmit the data, and we are having four modes of operations possible in I2c depending upon the speed: standard mode, fast mode, fast plus mode, and high speed mode. Standard mode means the speed is 100 kilobits per second. Fast mode means 400, and fast mode plus means 1 megabits per second. High speed means 3.4 megabits per second. So standard mode means if I am using master and the slave means both has to be present in same mode. If I am using standard mode here, it has to be present in standard mode. If I am using fast mode, then slave also be present in fast mode. If there is a change in the speed, it will create clock stitchings. Next, arbitration. Why arbitration is needed? We have already discussed I2c is supported for multi-master, multi-slave. For an example, I am having MCU1 and I am having MCU2. Both my MCUs are connected with single I2c line, and here I am having slave 1, slave 2 and slave 3. So 3 slaves we are having. So at a time master 1 and master 2 wanted to access my slave 1 or slave 2 means there is a racing condition between master 1 and master 2. So master 1 is also trying to send and master B is also trying to send. At this scenario, what will happen means 0 will have a dominant character and 1 will have a recessive one. For an example, this is my master. From the MSB we are sending. Okay, at the time what happened? Both master A and master B sending 1. So both are same priority. So both are using the bus. During the second bit, what happened? This is 1 and this is 0. I said 0 is the dominant one. So master B is the higher priority. So it wins the arbitration. It loses the arbitration because B is transmitting 0. So if anyone out of master 1, master 2, anyone is sending 0 means that will win the race and that uses this buses instead of the previous one. So it has a higher priority, it wins the arbitration and it loses the arbitration. This is how the I2c bus will be selected even though multiple masters are trying to access the same bus. So it is used for multi-master system. How it is working? Masters monitors the data lines. Which device is transmitting low will wins the arbitration. Even though master A and master B is sending simultaneously, the one which is sending 0 will wins the arbitration. By using we are using the arbitration, so it prevents our data corruption. Okay, if I don't use arbitration means both A and B will send, simultaneously access and sending data to slave 2 means slave 2 is not aware whether the received data is correct or it is received data. Slave 2 receives data from master 1 and master 2 as well as the same bus is connected to master 1 and master 2. So at the time some data loss or some data override will be happen. Okay, that will be prevented by using this arbitration condition. Next one is clock stitching. Clock stitching is nothing but our slave will hold the clock line as low. Normally, if some transmission is happen means at the end of the transmission, my clock line has to be released with a high level. Then only the transmission is correct. If my clock is pulled low means it denotes that clock stitching, which is nothing but it indicates that temporarily there is a pause in our communication. Okay, and why this is used means, for an example, in my system I am using master which is more faster when compared to slave means slave required some time to process the data. So at that time what will do means slave will pull the clock line as low till it ends the process and then it will release the clock line. Okay, hence what happen means once the process is done then only it release the clock. Afterwards only master will send the next set of information to the slave. Okay, this is about clock stitching. So here it is mentioned the slave needs more time to process the data and prepares for the next byte. So since it is holding the bus, master didn't send the next data till it receives the data. So what is the advantage of I2c? It is a simple wiring when compared to SPI. It has only 2 wire system as well as hardware cost is also low. I2c is supported in many devices. Most of the sensors are come up with I2c peripherals, and its expansion is also easy, efficient for short communication. Then what is the disadvantage? If you consider the speed of I2c, it is bit lower when compared to SPI. Even though SPI come up with a 4-wire system, the speed of communication is high in SPI when compared to I2c. as well as it is for short communication. So communication distance is limited in our I2c. If we are going for complex arbitration, means at that time my I2c would fail. Okay, as well as pull-up resistors are always required in our I2c communication. If the resistor is not pull up, then the transaction won't happen. As well as data transfer rate is low when compared to other peripheral communications. So this is a simple comparison between I2c and a SPI. Depending upon the wiring, I2c come up with 2 wire on a serial clock and a serial data, and the SPI come up with the clock data, MISO, MOSI and chip select. Then SPI is high, I2c will be moderate. And addressing, I2c come up with the addressing, whereas in SPI we don't have address. Instead of address, it uses the control select line to select which slave it want to communicate. Complexity is I2c is simple, whereas SPI is moderate. Why it is moderate? Because it is having 4 wire system, so it requires a bit complicated when compared to I2c. Multi-master support is supported in I2c, whereas in SPI it is the limited one. This is about the comparison of I2c and SPI. That's all about I2c. We will meet up with the next communication protocol. Till then, thank you. Bye.